This is a short video about integration techniques. It doesn't cover all of the integration techniques. It's just kind of a review of the main ones. The first technique is using area. You can graph the integrand and then find the area between the graph and the x-axis. So for example, I know the graph of the absolute value function. And so if I want to find the integral from -1 to 4, I'm finding the area of these two triangles. So it'd be 1/2 times 1 plus 1/2 times 16. The other technique is if you have a semicircle, we're doing the integral from -2 to 2. So we're doing the rectangle minus the semicircle. So, oops. So it'd be 4 times 2 minus 1/2 pi r squared, and r is 2. So that's the idea with using area. The second technique is knowing really well what your big 13 are, knowing that the antiderivative of 1 over x is natural log of x. Then you can find the antiderivative very quickly, and you can plug in your numbers. Here the antiderivative would be tangent inverse. And I'm going to stop there because I feel like that is a pre-calculus topic, but that's the idea. Make sure you have those big 13 down. That's something that you should definitely know cold going into your AP test. The third technique is USubstitution, which if you have the big 13 down cold, you are much better off because you're trying to turn this into one of the big 13. The way you can turn this into one of the big 13, well, you might look at it and say, oh, maybe it's 1 over x, and then it would be natural log. But if I make u equal to 1 plus e to the 2x, the derivative of that would be 2e to the 2x, and I don't have a 2x that's going to cancel. So that was a good thought, but that's not the u substitution to make. So luckily, I really have the big 13 down, and I know that this also looks a lot like tangent. So I could make u equal to e to the x, and if I do that, then du would be e to the x dx. So this integral becomes du over 1 plus u squared. So now it looks like tangent inverse. You really have to know the big 13 in order to make really good use of u substitution. The fourth technique is grab a calculator. Please don't hesitate to do that on the calculator portion of the test. It is totally acceptable and encouraged and necessary at times to calculate an integral with a machine. The fifth technique is integration by parts formula is u dv. The integral of u dv is going to be uv minus the integral of v du. The idea as you're trying to find u, you're going to use limit. And the idea with limit is you're trying to find something to be u that is easy to take a derivative of so that when you're choosing what to take an antiderivative of, it's not a terrible function. So as I'm choosing my u here, I'm going to start with logs. Oh, there is a log. So u is going to be natural log of x. That means the derivative would be 1 over x dx. And dv is going to be everything else. So dv would be x cubed dx. Antiderivative of that would be x to the 4th over 4. Now I set it up and I do uv minus the integral of v du. One of my x's can cancel, and I have something that I can do an antiderivative of. So the idea with integration by parts is you're trying to turn it into something that you can do an antiderivative of. So this would be x to the 4th, so that becomes x to the 5th over 5. You know you have an integration by parts problem if you have multiplication in your integrand. And it is not multiplication that happened because of the chain rule. Oh, I actually messed up here. Just to be super clear, this would be x to the third after I cancel the x, so then when I do the antiderivative, it becomes x to the fourth over 4. Sorry about that. All right, integration by parts is a tool for if you have multiplication in your integrand, or it could also be a tool for doing this integral. The multiplication is a multiplication by 1. When you're choosing limit, constants and x's count as polynomials. Technique number 6 is the partial fractions technique. A tip for when you might use partial fractions is if your denominator is factorable. That's a good tip off that it might be partial fractions. So if I rewrite this a little bit, I have 4 over x plus, x plus x plus 4 times x minus 4. And I know that before I added, I had a over x plus 4 plus b over x minus 4. And so if I want to figure out what a and b were, I find a common denominator. So I'd multiply the first fraction by x minus 4 over x minus 4. But I'm only looking at the numerator. And so b would be the second fraction I would multiply by x plus 4 over x plus 4. Now I can choose a smart x. So if I say x is equal to 4, I don't have any a's. So I have 8b equals 4. So then b would equal a half. And then I can do the same thing for x equal to negative 4. Then I have negative 8a equal to 4. So a would equal negative a half. And the purpose of this is now I have something that I can do an antiderivative of because I know the antiderivative of x plus 4, of 1 over x plus 4 is going to be natural log. I want to point out that I would have negative 1/2 natural log of x plus 4, plus 1/2 of natural log of x minus 4. You might sometimes see this rewritten as a division problem, so you might sometimes see it as 1/2 times natural log of x minus 4 divided by x plus 4, because subtraction can turn into division. So don't be freaked out if you see that the College Board does that trick. It's a way of simplifying the answer, and you might see it as a multiple choice option. So that's partial fractions. This is not meant to be every single integration technique. There is a longer College Board video if you want to see that. And this is meant to be fast so that you can say, hey, you know what, I need help with partial fractions, or hey, I need help with integration by parts. And you can go back and see those videos if that's something that you need help with. Okay, thanks so much. Bye.